Hello, I'm Rainer Kaltenbeck, and I'm going to talk about a potential future space mission to test the foundations of quantum physics. The central goal is to find out if we can observe quantum superpositions even with macroscopic objects. Will the predictions of quantum physics still be valid for very large masses? Will we be able to see interference as in a double-slit experiment? Or will we eventually see deviations from quantum physics, for example, due to gravity? For up to a few 10 to the 4 atomic mass units, it has been shown in experiments that there is good agreement with the predictions of quantum physics. But if we go to much higher test masses, the required free-fall time increases rapidly, and eventually such experiments may require a space environment. In 2018, together with the European Space Agency, we investigated the feasibility of such a space mission and under which conditions we could do that. One conclusion was that the space mission should orbit around the Lagrange point L2 of the Earth-Sun system, as is shown here. And to achieve the 20 Kelvin temperature that we require for these experiments, we plan to use V-grooves and a hydrogen sorption cooler. Here you can see the optical bench. The idea is that the test particle is trapped here, and then we observe matter wave interference along this axis. In order to actually implement such a mission, we still need to do some technology development, and we need to face a few critical challenges. The good news is that a short time ago, Uro Stelic and the Aspermeyer group demonstrated for the first time that it is possible to cool an optically trapped particle into the quantum ground state of motion. The three remaining critical challenges we face is to achieve the vacuum requirement, which is ideally 10 to the minus 15 millibar, and to load and to characterize particles in our optical trap, and to ensure that the optical means we use to prepare our quantum state will not at the same time destroy our quantum state. This last point has been investigated in a paper we published recently in 2019. In the full presentation, I will also discuss some additional recent work on implementing adhesively bonded cavities and some efforts to optimize the thermal design of our mission proposal. Thank you for your attention.